much for the nice introduction. So actually I won't talk today about a time-dependent problem, it will be stationary. And it's related to superconductivity, and the underlying model is the Ginzburg-Landau model. Yeah? And I can relate a little bit to the previous talk by Daniel, because we will have an energy minimization problem, and there will be some kind of LOD involved in that, which is hidden in this term here, multiscale technique. So how does it work? So, and I should mention that this is work, collaboration with Patrick Henning, so my supervisor in Bochum, as well as a colleague, Benjamin Döding, who was also some time in Bochum, and is now in Karlsruhe, and a student of Patrick Maria Bluth from Bochum. So the first slide is about the motivation, which is the superconductivity. So superconductivity is, in a sense, a quantum mechanical phenomena that describes the property or the phenomena that certain materials lose their electrical resistance at very low temperatures. And this effect or phenomena was first discovered by a Dutch physicist, Heike Onnes, in 1911. And as I said, it is a quantum mechanical nature underlying this phenomena, but already in the 1950s, Ginzburg and Landau came up with a macroscopic description of this phenomena, the famous Ginzburg-Landau theory that I'm going to talk about. And it essentially says what is hidden in this diagram here. So you have here on the x-axis the temperature of some material block, this square here. And on the y-axis you have a magnetic field that you apply to this block, and this is indicated by these arrows here in these pictures. So when at normal temperatures, so let's say room temperature, we are in this phase C here, which is the normal state. Yeah, so there the material has electrical resistance, and if you apply a magnetic field to this, it just can pass through this material according to Maxwell equations or something like this. Okay, so, and if we go down, so we cool this block now down, and then we pass some critical temperature Tc here, and then this material instantly moves into the perfect superconducting material state, which means that it loses its electrical resistance. And if you then apply such a magnetic field, the so-called Meissner-Ochsenfeld effect occurs, that this magnetic field is actually totally expelled by the superconductor, and this is a perfectly superconducting state. Okay. But in 1957, Abrikosov figured out that between these two phases, there's another third phase that occurs for this so-called type 2 superconductors, whatever they are. And this third phase is this region B here. So when you strengthen the magnetic field or heat up the temperature a little bit, this magnetic field that you apply to this superconductor actually starts to penetrate this material. And due to the quantum mechanical nature of the whole process, this occurs at quantized vortices that you see in an experiment here in this picture. And these are actually the interesting states that I want to consider in the following. So enough about physics for the moment. Let's dive into the mathematics, which is the Ginzburg-Landau model. So here again we have this block of the superconducting material. It's denoted by omega, and I would assume for simplicity it's a convex domain in up to 3 space dimensions. So you can also write this problem down into 2 space dimensions. Actually the numerical experiments that I will show you are only in 2D. But the theory works for 3D as well. So, and then the Ginzburg-Landau theory tells you that the superconductor is described by a minimizer, U and A, of this Ginzburg-Landau free energy that you see here. So what are these minimizing arguments? Well, I have this U here, it's a complex valued function. It's some interpretation of a quantum mechanical wave function, and it's called the order parameter. And the actually physical observable is the density of this order parameter, yeah? And what it says, if its density is 1, then the material is in a superconducting state in this area. And if it goes down to 0, it's in a normal state, non-superconducting. And the second argument here is this vector field A, which is just the electromagnetic vector potential within the superconductor. So there the physical observable is the curl of A, which describes the magnetic field within the superconductor. And the Hx here is this external magnetic field that we apply to it. Okay, let's have a brief closer look onto the energy. So it consists of a kinetic part here involving the gradient of U, the vector potential A and U as well. And there is a brief factor 1 over kappa here that will play a crucial role in the following. Namely, this kappa is a parameter, a material-dependent parameter called the Ginzburg-Landau parameter, and that's the parameter we want to vary in the following. The second term here is a nonlinearity, involving only the U. And then you have this curl A minus H term here, which is essentially something like Maxwell equations, and some gauging involving this divergence term. Okay, that's the system that I want to consider. We want to minimize this energy here. So here you see some examples of minimizers that I just computed for several values of this Ginzburg-Landau parameter kappa, running here from 10 on the left to 100 on the right, and you actually observe these vortex structures that I talked about, and they form in the order parameter. So shown here is the density of the order parameter, and what you observe is as you increase the value of kappa, this number of vortices, they increase as well. Their size shrinks somehow. And of course, if you want to resolve this now with a suitable numerical method, you need to have a sufficiently small mesh to resolve actually this vortex pattern. And that's what we're going to do. And this naturally imposes you 2 questions. Namely, can we quantify the resolution condition dependent on this parameter kappa? And the second one is, where the LOD will come into place, is what are good approximation spaces that maybe can relax this resolution condition. And that's where we will set up the LOD framework for. I should note that in the picture before, there was just the density of the order parameter, but in the order parameter itself, there's much more structure in there. So shown is here the real part of it. So it's not just these vortices that it goes down to 0, but there's also some complex oscillation. We should keep this in mind, and I will come back to it. Some overview about the literature. Of course, this model is quite old, from the 1950s. A lot of scientists has worked on it. And I just want to note that there is these seminal works here from the early 90s by Ginzburg and Peterson, where they treated the well-postness property of this model, as well as standard finite element approximations. They observed optimal order of convergence, all the nice things. However, what they did not do is tracing the dependency on this parameter kappa. There has been also finite volume methods and co-volume methods, also in works around Chengdu. And there is a much larger literature. What I want to note is about the time-dependent Ginzburg-Landau equation, which is essentially if you take this energy and set up the L2 flow of it, or the Schrödinger flow. And in 24, my collaborators Benjamin and Patrick, they started then to recap this work here by Ginzburg and Peterson, and then developed an error analysis that actually traced this dependency on this parameter kappa. And I will recap a little bit of it. And Patrick and Théophile Chaumont-Frélé, they also refined the analysis there regarding to higher order finite elements. Okay, so some preliminaries about the well-postness. It's rather straightforward to prove that there exists at least one minimizer, which you can find in this seminal work by Chengdu and co-authors. And this minimizer actually needs to be divergence-free in A due to this penalty term of the divergence that I introduced in the energy. And for that reason, it also needs to have a zero normal trace. And since we're looking for minimizers, this minimizer needs to satisfy the critical, needs to be a critical point. So the derivative of the energy needs to vanish. And if you write this down, you observe the very famous Ginzburg-Landau equations that look like this in some strong formulation in this setting. Okay, so existence is guaranteed. What about uniqueness? Well, this is a little bit more involved. But first, considering this vector potential A, so as I said, due to this penalty term of the divergence, the minimizer is actually divergence-free, which physically means that we're working in the Coulomb gauge. And so that is actually the space that I want to consider as H1 with some zero normal trace of the vector potential. And we can assume somehow under some conditions that or if the system is not degenerated in the case, this minimizer in A should be at least locally unique. However, in the order parameter U, it's a little bit more different because there is a symmetry hidden in the energy. Namely, I can rotate any minimizer with some complex phase and it's still a minimizer. Yeah? So actually, there is a whole manifold of minimizers, if I found one, which means that there is a neutral mode of the second Fouché derivative, which is the generator of this manifold, which is IU in the order parameter. Yeah? So we need to keep track a little bit of this neutral mode, and we will block it. And what we then assume is about the minimizer is that the spectrum of the second Fouché derivative at the minimizer is actually positive if we block this neutral mode in this fashion here. Okay, some technical details here about this blocking the neutral mode. However, what this actually means is that this minimizer is assumed to be quasi-unique, at least locally. Okay, now I want to simplify a little bit this model first. Namely, I want to assume that this vector potential A is given, and we only minimize with respect to the order parameter. And actually, as we will see later, this order parameter is also the real interesting quantity, to be honest. So in this sense, we assume that this A is a bounded vector potential, which is divergence-free. Then the whole problem reduces to minimizing this energy here with respect to U in H1. And what you can prove is that this minimizer actually needs to be H2 regular. You can prove that it has magnitude between 0 and 1, which is in line with its physical interpretation of the density of this Cooper pairs, these electrons. And what the important observation is, if you consider the L2 norm of it, you can bound it independent of kappa and any, later on, there will be also mesh sizes involved. So this tilde notation here means there is some constant independent of kappa, in this case, and later on also independent of some mesh sizes. But the gradient, it scales with kappa, and the second derivative scales with kappa squared. Yeah? So that's similar observations as you would make do in something like Helmholtz problems or so that people might be familiar with. And for that purpose, I will introduce a kappa-weighted norm that scales or traces the scaling in the gradient correctly, yeah, by adding this factor 1 over kappa here in front of the gradient. So this is a proper energy norm that we will use. And the first observation that we make is from this assumption that the minimizer is quasi-unique. You can actually observe that the bilinear form induced by the second derivative here is coercive. Meaning there is a coercivity constant denoted by 1 over rho. And this coercivity means with respect to the H1 kappa norm here. But the important observation is that this rho here strongly depends on kappa. Namely, the coercivity constant goes to 0 as kappa goes to infinity, or in other words, the rho goes to infinity as kappa goes to infinity. But this is what we just observe numerically from our experiments, and we conject somehow that this scales with some power in kappa. But we are not aware of any proof or rigorous justification of this fact. However, what I did here is I computed the spectral gap of the second derivative, more or less, independence of kappa for certain minimizers, and you see that it actually decays here. And if I fit this data, I observe something like it decays with 1 over kappa to power 2 or 3. Yeah? We just have to keep this in mind, that this rho here gets very large as kappa gets large. There is some active research in the analysis community going on about this problem, and at least for the magnetic Laplacian, which is this operator here, which is more or less the principal part of this second derivative, you can prove in some settings that the spectral gap here needs to decay with 1 over kappa, yeah, which would correspond to alpha equal to 1 here. Yeah? So this indicates really this property. Okay. So let's have a look onto the numerics. Yeah? Let's first consider standard finite element approximations. So I take a nice mesh of mesh size h greater than 0. Consider standard linear Lagrange finite elements on it, conforming. And this space is denoted by VH, as in the previous talk, more or less. And then we have to intersect again or block this neutral direction. And this is indicated by this bot here. Okay. So if you consider a minimizer U and try to figure out how well it is approximated in the space, you apply the standard error estimate framework. And what you observe is that the best approximation error is bounded by kappa times h. Yeah? So this supposes you at least the resolution condition that your mesh size needs to be smaller than 1 over kappa. However, as Benjamin Döding and Patrick Henning figured out in this work from 24, the situation is a little bit worse if you consider the discrete minimizers. So here I take a discrete minimizer which is characterized by minimizer of the energy over the approximation space. And then we can find an exact minimizer close by if the h is sufficiently small. And the error of this discrete minimizer is bounded by the best approximation. But there is a prefactor involved here, this namely 1 plus rho kappa h. And there this rho is popping up, yeah, which gets very large. So and then if I apply my best approximation estimate, I observe optimal order of convergence in h, linear scaling in kappa, in the asymptotic, let's say asymptotic leading order. But there is this additional higher order term that needs to be compensated if you want to have your numerical solution to be suitable or a good approximation. Yeah? So this needs to be small, which means that your h actually needs to be smaller than 1 over square root of rho times 1 over kappa. So this is a stronger resolution condition. And now you might say, okay, this is somehow an artifact from the analysis, from the error analysis, but you can actually observe this additional resolution condition numerically. So on the left-hand side here, you see the best approximation error. Yeah? So I computed an exact minimizer on some fine approximation space and then projected into a coarser finite element space. And we nicely observe first order of convergence as expected for different values of kappa. And if you note here, the error itself is scaled with 1 over kappa, so which means that these lines somehow more or less are on top of each other, which means we are also tracing the right scaling in kappa. But on the right-hand side, you see the actual discrete minimizers that I compute, and you see here this significant pre-asymptotic regime here on the right, where the error does not decay initially. And just if you resolve something, then you obtain the optimal order of convergence. Yeah, and this pre-asymptotic regime here can be traced back to this additional error term here. So there is some kind of a pollution effect. Okay, so this was, go back maybe, this was the answer to my first question, namely, can we quantify the resolution condition independence of kappa, at least for standard linear Lagrange finite elements. Yeah? You can do this also in a general framework. The analysis for it actually just needs to be some assumptions on the approximation space. So it generalizes to higher order finite element spaces. Okay, so let me come to the second question that I raised. Can we define a good approximation space in the spirit of the topic of this workshop? So what is a good approximation space that maybe relaxes this resolution condition? So, so since we have this factor kappa that somehow governs the size of these vortices that we want to resolve, this is some kind of a multiscale or monoscale parameter. Yeah? So that's the reason why we might think of picking a good approach for multiscale problems to test if this might be a good idea to get a good approximation space. Yeah? And there will be the LOD coming on the next slide. So, and to define it, we first need to pick a bilinear form that has something to do with my problem, and I define this A beta here to be the principal part or the kinetic part of my energy, and I need to stabilize it a little bit with a little bit of mass, yeah, that is given by this factor beta here, the stabilization of mass, yeah. So, and why do I need the stabilization? Well, to make this bilinear form coercive, I need to make the beta sufficiently large here, and then I obtain coercivity of this bilinear form on H1 with respect to the H1 kappa norm. However, if your mesh size is sufficiently small, sufficiently here means like 1 over kappa, which we need anyway for resolving the vortex pattern, then we obtain coercivity of this bilinear form on a subspace, namely the space W here, which is the kernel of the L2 projection. Yeah. So, and now I come back somehow to the previous talk where we also had this detailed space. I think this space involves somehow or includes the fine oscillations or fine scale structures that the standard finite element space actually cannot resolve. However, we obtain coercivity for any beta, and in particular without any stabilization. This will be important for the next steps. We want to include the case beta equal to 0 in particular. Okay, now I define the multiscale approximation space in the spirit of the localized orthogonal decomposition, and I should mention here Axel Marquis and Daniel Petersheim, who were in the audience, that developed this approach in 2014. And there's additional literature we also had in the previous talk. And this space is defined to be my standard finite element approximation space corrected with some C beta here. And what is this corrector C beta? Well, it's in a sense just a projection of the standard finite element space onto this detail space with respect to the bilinear form A beta. This is the notion that I use, and in the case that the beta is sufficiently large and this A beta is an inner product, you can characterize it as Daniel did like this here, yeah? Where the A minus 1 is a solution operator with respect to this bilinear form. Yeah. So, and what was the idea behind that? Well, usually you have, in the standard Lagrange finite element setting, you have a decomposition of your solution space into the approximation space and this detail space W with orthogonality with respect to L2. And the idea of this LOD is that you now define a new approximation space that is orthogonal on that detail space W with respect to this inner product that you choose, yeah? Which is somehow problem adapted. And the trivial observation is then that the dimension of the new approximation space does not change. Okay. So here is how such basis function look like in this Ginzburg-Landau setting. So again, we have here the real part of some minimizer that I computed. And here on the left, there is our standard head function that I take to construct the LOD space. And the pictures on the right here are the real part, in our imaginary part of this new basis. And you see that this basis involves somehow these wiggles of the actual solution. Yeah, so you might guess, okay, this might be a good this is a good basis to approximate this solution. Okay, of course we can quantify this mathematically. So let's take an H2 regular function and consider this elliptical problem here for this function B. So it's a solution to it for some right-hand side f and L2. And now I can take a projection onto the multiscale space that is defined in this fashion here. So I project in first towards the standard front element space and then subtract the corrector of it. And due to time constraints, maybe I will skip the actual proof. That's the standard LOD trick that is familiar to, what's that, Daniel? Maybe 30% of the audience, I don't know. However, the outcome is that if you consider the error of this projection into the LOD space, you can bound it by a factor kappa times h times the error of the L2 projection into the classical finite element space of the right-hand side f. And if we now, in addition, assume that the f is a little bit more regular, you can apply standard estimate and obtain third-order convergence in h, scaled with kappa. But however, there is still the H2 norm, or H2 semi-norm of the right-hand side f here. Okay, that's the error estimate that we use. Of course, we apply this now to our minimizer, which is H2 regular, and it actually solves this problem with this right-hand side here, which is also H2 regular, as you observe, and you can bound the L2 norm with a prefactor 1 plus beta. Forget about this, but important is here that you get another two factors of kappa. So this results in a best approximation estimate in the LOD space with respect to the H1 kappa norm, which is then third order in H, as we expect, but also a cubic scaling in kappa. Yeah, plus this prefactor 1 plus beta. And there you see, okay, why do we want to choose beta as small as possible to make this estimate as good as possible? Yeah, so that's why we were including the case beta equal to 0. Yeah. Okay, so, and from there we can conclude now, if we consider a discrete minimizer in this LOD space, then there is again an exact minimizer close by. The error is bounded by the best approximation error involving this prefactor again. If I then apply my best approximation estimate, I obtain these error estimates here. So optimal order is 3 in H and cubic scaling in kappa. But again, we have an additional factor that needs to be compensated. But now this one is actually weaker to be compensated because of these higher orders. So now H needs to be something like 1 over fourth root of rho times 1 over kappa. Yeah? So in that sense, we can relax this resolution condition. Again, we can do this numerically. So left side again, best approximation, nice convergence, almost without any pre-asymptotic effects. Yeah? There is still the resolution condition hidden in the best approximation that H needs to be smaller than 1 over kappa. Why you see this here. However, it very fast strongly converges here. to a third order in H, and again we scale with kappa, everything is more or less on top of each other, so we trace the right scaling in kappa here. And on the right hand side, the picture is again more complicated for the discrete minimizers. So we observe again a pre-asymptotic regime where this additional error term is not yet compensated. We need to compensate it, then we obtain the perfect, good approximation order. And in the end, you see a stagnation regime, which is of course due to the localization of the LOD. So I use the LOD in an idealized setting where we do not localize, but of course in practice you need to localize to get a feasible method. But yeah, this was already mentioned during this week. I think I don't have to go into the details here. And okay, there is still an asymptotic, pre-asymptotic regime, but if we compare now the LOD resolution condition to the finite element from the very beginning, you actually observe that, okay, I first need to mention here, so dashed is the best approximation again, solid is the discrete minimizer, so the LOD is pretty fast in a line with this best approximation property for the same mesh sizes compared to the finite element approximation where the error is even bigger. Yeah, it's just a more resolved, zoomed in plot. Okay, if these error plots are not yet convincing enough for you, I also have some nice pictures. So we compute the discrete minimizers here with standard finite elements for only a few degrees of freedom. Yeah, so 25 degrees of freedom here on the left, and about 1000 degrees of freedom on the right. And you see in the beginning, of course, you do not see anything, and you need this 1000 degrees of freedom to actually resolve somehow this vortex pattern that we are interested into. So let's have a look how the LOD performs. Well, only with 25 degrees of freedom, which is really just a few degrees of freedom, you roughly observe the vortex pattern. Yeah, so there is already the right number of vortices, although the structure is a little bit dislocated. Anyhow, if we add a few degrees of freedom, then we observe more or less the correct vortex pattern. Yeah, so this somehow should highlight you that this is a nice approach to do so. Okay, some practical aspects. I have one slide about this. So as I said, the usual basis functions, they are not locally supported anymore, but as we have seen in the picture and what the standard theory predicts is that these basis functions, they decay exponentially, so you can boil down the computation of this basis function to local patches here. That's indicated by this picture here, and we have a full error analysis available with respect to this localization error, also independence of this factor kappa here. In a sense, what comes out is that the number of layers that you need to choose are proportional to the logarithm of kappa. That's more or less the outcome of this error analysis, but I do not highlight this further. And of course, this basis function needs to be solved on some fine mesh size, which also introduces additional error on the small scale. I just told you something about the approximation properties and not how to compute it actually. And now I refer a little bit to Daniel's talk, where we had this kind of gradient descent or steepest descent method that you can use to actually compute such a minimizer. They again have this form, and this descent direction you can choose again as an L2 gradient or metric driven Sobolev gradient if you want, or also conjugate methods. Although I have to say, in comparison to the previous talk, we do not have a constraint minimization problem, so there is actually no eigenvalues involved or so, yeah? But the framework essentially you can use here as well. Then the limits of such descent methods are only local minimizers. Yeah, so we have a non-convex optimization problem. So the best you can hope for is obtaining a local minimum, and actually physicists are interested more in the global minima. However, the theory that I just showed you also applies to local minimizers. Yeah, so there you can just live with a first order optimality condition. Yeah, but you can actually do the same theory there. Okay. Now I want to come back in the last 10 to 15 minutes to the full problem. Yeah, so we simplified the problem to the fact that we assume that the A is already given. Yeah. But actually it's unknown. Yeah? The only thing that is given is this external magnetic field H here. So we come back to this full Ginzburg-Landau free energy. Just briefly recap what I had on the first two slides. There exists a minimizer. We assume quasi-uniqueness, which now means that the spectrum of this second derivative here is bounded away from zero. We block a neutral direction. And if the external magnetic field here is sufficiently smooth and we have a nice domain, let's say a cuboid for simplicity, we can actually prove that the minimizer is H3 regular in both components. Yeah? And again, we obtain coercivity of the bilinear form induced by the second derivative here, again involving this coercivity constant 1 over rho. That gets very small for large kappa. However, the LOD construction I showed you relied on the fact that we know the A, yeah? So the bilinear form that I chose was fixed once I know such an A, or it is based on knowing the A, which I do not know a priori if I want to solve the full problem. So what's the idea? How can we overcome this problem? Well, we just take any vector potential that satisfies some assumptions. Namely, it should be divergence free, okay, and I want to bound its norms in H2 and H3 according to these expressions here. Of course, you might think of choosing this A star as a rough approximation or a good approximation of the actual vector potential, which is the minimizer. So what we do in practice is we solve numerically in an offline phase this curl problem here, which minimizes, I go back to the energy, which is a minimizer of these two components here. Yeah? So we could solve this quite easy with a certain numerical method. However, of course, and then this is a solution of this numerical method won't be H3 regular in general anymore. However, you can do the subsequent error analysis that I show you on the next slide, where plus additional error terms involving the error to the actual minimizer A measured in H1, let's say. Yeah? So if you make this small here, then you won't see the errors caused by this approximation. So how does a full discretization then look like? Well, I now construct the LOD space for my order parameter, which is now this expression here where this corrector has now sub-index A star, indicating that this depends on the choice of this A star, and the construction is based on this bilinear form where here again the A star pops up, and I now fully neglect the stabilization, which is not important anymore as we have seen. And this I do on a mesh with mesh size capital H. Okay? And for the vector potential, we know it's H3 regular in certain cases. Then we can take, for example, a classical P2 Lagrange finite element approximation there on a mesh, which is now has the mesh size little h. Yeah, so there are two different meshes involved here. But actually, it's not that important what you choose for the A. You can say take P1, or maybe if you work on non-convex domains, you might take Nedelec elements or something like this. Yeah, so it's all what we did this also, and you can do it essentially. And then my problem that I need to solve numerically reduces to minimizing the energy on these approximation spaces, and that's the characterization of a discrete minimizer. So, and basically we can extend everything from the previous theorems to this full problem where we minimize with respect to U and A. So if everything is nice and smooth, and we have small mesh sizes, then there is a discrete minimizer close by a unique exact minimizer, and we can bound the error of this discrete minimizer in H1 kappa, so measured with respect to H1 kappa in the order parameter, and just with H1 in the vector potential by the optimal order of convergence 3 in the order parameter, again scaling, cubic scaling in kappa, plus this optimal order here for the vector potential, which is 2 with respect to the mesh size, and there is only 1 kappa popping up here in this error estimate. So this indicates that the structure in the vector potential is not that sensitive to variations of kappa. Yeah? That's what it actually means. And again, we have an additional higher order term here that needs to be compensated. So, and this imposes you then resolutions conditions for both components, the U again, which is more or less the same as in the simplified model.
2 minutes
yes.
to wrap up.
Okay. And another one in for the vector potential, yeah, which is weaker than the one in the order parameter. So we can do numerical experiments as well. So the left here we see again our nice minimizers in the order parameter, where you see now the vortex patterns, and on the right you see the vector potential that we compute, and here is the curl of the vector potential shown, and these are variations for different values of kappa, and I only show you one vector potential for A because for the other values they would look exactly the same. Yeah, on this. So there is not much structure in this vector potential included here. We can do error plots as well. We observe again nice convergence polluted by different errors in the order parameter, and obtain convergence in the vector potential in A. However, there is no scaling with kappa here, and we are really we really do not know if we are optimal here in this kappa scaling in the vector potential. But in the analysis it boils down that the H3 norm of the vector potential we can bound only by kappa. So this involves this factor here, although the numerical experiments indicate that this shouldn't be there. Last minute, I tell you something about the choice of the A star. So practically we chose the first option here, but you can also choose just A star to be 0, which is the second one here, and we compared it to the optimal choice of the actual minimizing A. Yeah, and we did an experiment here for these two values of kappa again. One is now dashed and one is solid. And you see the red curve, which corresponds to A star equal to 0, performs a little bit worse, but it still has the optimal order of convergence. Yeah, so we have still third order of convergence in H, although there is actually no A star chosen. Yeah, so the LOD space in that case is only constructed with respect to the Laplacian in a sense. Yeah, but this is sufficient to obtain the third order of convergence. And and our practical choice performs in a sense as good as the optimal one of choosing A star to be the exact minimizer. That's what we observe. Okay, let me conclude. So, I showed you something about the Ginzburg-Landau model in superconductors in the so-called high kappa regime. I proposed a multiscale approximation space in the spirit of the LOD. We obtained a high order of convergence and can actually weaken this resolution condition on the mesh sizes. We studied this simplified model as well as the Ginzburg-Landau, the full Ginzburg-Landau model, and there is a full kappa-dependent error analysis available. So in the future works, we want to consider gradient descent methods that I just highlighted very briefly there. For there, you can also, or we hope we can do also a kappa-dependent error analysis for the convergence of those. But all these gradient descent methods, they rely on the fact, okay, how to choose this initial value, where do you start, and this highly influences to which minimizer you actually converge to. And one idea is to use some kind of machine learning or neural network approaches to get good guesses for the initial value. And then on the long run, there might be also an extension to multi-component superconductors, which also exists and are of interest in physics. So it's my last slide. There are the references where you can find all this, and I thank you for the attention.